So the next talk is actually, it connects very well with the work that I just presented, and it's yeah, actually based on some of the insights we had in the paper that I just presented. We generalize now abstract dialectical frameworks. Yes, so I'll present very shortly abstract dialectical frameworks. This is basically the slides I had before, so everyone knows this now very well. And then I'll tell you about how we generalized ADFs to what we call CADFs. First, I'll talk about the syntax, and then I'll talk about the semantics, which was again the hardest part. And then I'll tell you something about what we call the grounded state, which is a unique grounded interpretation, which is where we had to do some more work to guarantee uniqueness and existence. Okay, so abstract dialectical frameworks, we already talked about it. These are these directed graphs where the interpretation of the directed graph is determined by these conditions. And we also talked about the semantics using this gamma function or the completions. So yeah, unless anyone has questions on this, I just tell you again that these complete interpretations are fixed points of the gamma function. That's really the important thing. And then completions, I think we talked amply about in my last talk. So the idea is to have these interpretations which are fixed points of the gamma function. That's what we are interested in. Okay, so conditional ADFs, the syntax. So we started, or we were working quite intensively on ADFs. And then we observed that this ADF, it's defined as a set of statements, links between the statements and the conditions. But actually, if you have the statements and the conditions, you can actually derive the links. So the links are kind of superfluous. You can come up with the links based on the conditions. And so you can also define an ADF as just a set of statements with conditions. And then if you think about it that way, an ADF is actually a set of statement condition pairs where we have, so we use then this symbol. It's not used in the literature on ADFs, but we introduced it. So for every statement S1, for example, we have that S1 can be accepted if the condition of S1 is accepted. And then if you phrase it like this, it seems, so the only restraint really is that this Si is an atom for every I. So every atom comes with the condition. And if you phrase it like this, at least to us, it actually became quite useful or quite interesting to see what happens if instead of having an atom here on the left-hand side, we also have a possibly complex formula on the left-hand side. And so we call this conditional abstract dialectical frameworks. It's just a set of acceptance pairs which say that phi is accepted if psi is accepted. And here is an example which shows how much more you can do when compared to normal abstract dialectical frameworks. Now we can say, for example, that P or S or Q is accepted if top is accepted, or P and S is accepted if not Q is accepted. So the nice thing we can do here is that we can represent, for example, form of non-determinateness. So for example, we don't have to say that some node attacks or supports a single other atom. No, we can say it supports a set of atoms, so to say. That's what's going on here, for example. So yeah, you can accept, you can express a lot more in these conditional abstract dialectical frameworks than in normal abstract dialectical frameworks. This is the syntax. But then, of course, the challenge is how we can we generalize the semantics, which we talked about before, to these more complex formulas. And the first idea which one might have is that we can generalize these three-valued complete interpretations as follows. So before we had that interpretation of a node had to be the same as the interpretation of its condition. So we could just say, okay, now for every acceptance pair, the truth value according to V of the statement should be the same as the truth value according to V of the condition of this statement. So we just say that truth value of phi should be the same as truth value of psi for every acceptance pair in the conditional ADF. However, this doesn't really work because, for example, it gives rise to ADFs where complete interpretations might not exist. For example, if we say that P has to be accepted if top is accepted and not P has to be accepted if top is accepted, then then it's not very hard to see that there exists no interpretation which sets both P and not P to the truth value of top, namely true. So here, by the way, you also see that CADFs, for example, allow for an overdetermination of information, because now we can give some acceptance condition for P as well as for not P. But there might not be complete interpretations if we define complete interpretations in this way. And the idea there was to move from a three-valued interpretation, or how we solve this is to move from a three-valued interpretation where we have true, false, and undecided to a four-valued interpretation. So now we see once more the value of the four values. And so now we have also inconsistent as a fourth truth value. And this is a graph that people familiar with bilattices know very well. So we have the two orders on this truth values. The first one is the information order, where we already saw that true and false are more informative than undecided, but now inconsistent, it's more informative than both true and false. And then we have the truth order in this direction, but that's less important. The main order we use here is really the information order. And so now we generalize the set of interpretations calligraphic phi as mappings of atoms to four truth values: true, false, undecided, and inconsistent. And now, of course, the challenge is to generalize this logic based on completions to four valid interpretations. How do we do this? Well, it's kind of a two-stage process now. So we define the set of completions, which now will be a set of sets of interpretations. So a set of sets of possible worlds in a two-step process. So first we want to somehow eliminate the truth value inconsistent. And the idea is that for every, so we start with a four-valued interpretation, and then we take as the set of three-valued completions, we take all the interpretations which are obtained by replacing inconsistent with either true or false. Here's an example. Suppose we have the interpretation which maps the first atom to true, the second one to undecided, and the third to inconsistent. Then the set of three valid completions consists of TUT, because we replaced here inconsistent by true, and TUF, because we replaced inconsistent here by false. And so the idea is that the four-valued interpretation, it represents somehow an overdetermination of the truth values. And so we want to split up this overdetermination in two interpretations which jointly express the information available in this four-valued interpretation. And then the second step is the following. So now we go from this three-valid completion to what we then call the four-valid completions. And there the idea is that we take all of these three-valid interpretations in our set of three-valid completions, and we just take the set of two-valid completions of every interpretation. And so now we end up with a set of sets of two-valid interpretations, because for every three-valued interpretation, now we take the two-valued completions and we keep them, of course, separated. So here TUT becomes TTT and TFT, whereas TUF becomes TTF and TFF. So the idea is that these two-valid completions, they represent candidates of the three-valid interpretation which we had before, And then the sets of two-valued completions together represent the information given by this possibly inconsistent interpretation. And so we obtain this, what we call four valued completions in a two-step process. First, we go from one four valued interpretation to a set of three valued interpretations. And then we go from this set of three valued interpretation to a set of sets of two valued interpretations. And then we can assign truth values, rather straightforwardly. So if we have, so to say, full agreement on a truth value of a complex formula, we assign it true or false. So now we kind of have to look every set of two valid interpretations. If for every set of two valid interpretations, the consensus of this set is true, then we assign true to a complex formula. If for every set of completions in this four valid completions, so every set of two valid interpretations, the consensus is false for a complex formula, then we assign F. And if we have contradicting information, so we have at least one set of two valid interpretations which assigns where the consensus is true, and one set of two valid interpretations where the consensus is false, then we assign inconsistent to this formula. And otherwise, we assign undecided. So here is an example. It's the example we had before. We calculated the set of completions. And for example, we see that the truth value of A and C is inconsistent because we have here one set of two valid interpretations which assigns true, namely this one, and one set of two valid interpretations which assigns false, namely this one, because here A and C is false. And another example is that B and C is undecided because, for example, we have here that there is one set of two valid interpretations which assigns undecided. And so that's how this logic works. It's a generalization of this logic of completions, which we saw in the previous talk, now to four truth values. Now we have this two-step process, so everything becomes a bit more complicated. Yes, and now we are almost there for our semantics of CADFs. What we did next was to define the gamma function. So the gamma function for a CADF, it maps a four valid interpretation to now a set of four valid interpretations. And I hope I'll make clear why we need now a set. So remember, before the gamma function, it took as input an interpretation and gave as output a single interpretation. Now we have as input still interpretation, even though it's four valued. And as an output, we have now a set of interpretations. Which interpretations? Well, it's the information order minimal ones, which set for every acceptance pair phi, if phi is accepted. If psi is accepted, which set the statement phi at least as informative as the truth value of this input interpretation assigned to the condition of this acceptance pair. And so this can be more than one interpretation which does that, and which one do we take? Well, we take the informationally minimally one. And so this this gamma function, it generalizes the gamma function from ADFs. It's non-deterministic in the sense that we can input a single interpretation and we can output a set of interpretations. And it's approximate in the sense that before we could set our gamma v to exactly the same truth value as our input v of the condition. And now sometimes we have to go a bit higher because we might have actually, there might be some acceptance pairs where the statements have some atoms in common, and then we might have to go, for example, if one says true and one says false, we might have to move to inconsistent. So it's a generalization that's non-deterministic and approximate. So here is an example. Of course, I won't walk you through all of the interpretations, but I'll just pick out one. So we have a conditional ADF where the first acceptance pair says that P or S can be accepted if top is accepted, and the second pair says that not S can be accepted if P is accepted. And now we look at this interpretation TF, for example, and we see, okay, since here we have P or S, then top. And of course, because we preserve tautologies, the interpretation TF sets T to top. So we know that P has to be true, or, well, more informative than true, or S has to be more informative than true. And then we look at the second acceptance pair, and there we see that since P is true, we also know that not S has to be true. So this means that S has to be more informative than false. And then we see if we combine these two conditions, we get as the two informationally minimal candidates, we get these two. For example, here we ensure that P is true and that F is false. And here, for example, here you see an example of where we have also an approximate behavior of our gamma function. We see, for example, that since we choose S to be more informative than true and S to be more informative than false, then we see that S here has to be inconsistent. So that's how the gamma function works. And then, yeah, since we have put all the work in the gamma function, we can define the semantics of these CADFs quite straightforwardly. So again, we define admissible semantics or admissible interpretations as prefix points in the sense that an interpretation is admissible if there is at least one interpretation in the outcome of the gamma function applied to V, such that V is less informative than V prime. We say that V is complete if and only if V is an element of the application of the gamma function to itself. So notice that now, because gamma maps one interpretation to a set of interpretations, of course, we also had to change here a bit the conditions for being a fixed point. And then preferred and grounded are defined as usual, so as the informationally maximal or the informationally minimal interpretations. Yes. And so here is an example of what are the admissible interpretations. For example, undecided. Undecided is an admissible interpretation because it's less informative than both of these actually interpretations in its gamma outcome. And then we see, yeah, for example, UT is also admissible. In fact, it's actually complete because we have here the witness UT. So in fact, the complete ones are these two. We have UT, which is a part of its own gamma function or of the gamma function applied to itself. And we have TF, which is part of the gamma function applied to itself. And yes, these two are also preferred and grounded actually. Yes, and then one of the main results of the paper is these properties of the semantics, and basically we could show existence of all of the semantics under the assumption that a CADF is well formed, which means that for every interpretation, if we apply the gamma function, it's not empty. And we could also show something which is in argumentation or also abstract dialectical frameworks also nice to have, is that the preferred interpretations are a subset of the complete interpretations under some additional assumption, which is not so important now. So yeah, that's the nice thing about this admittedly somewhat complicated way of defining gamma, is that we can ensure existence of all the major semantics. However, one little thing that we noticed when looking at or when seeing which properties generalize from the abstract dialectical framework case to the CADF case is that the grounded interpretation might not be unique. Sorry, this should be not exist, but unique. And this can be very easily seen if we have, for example, the CADF just consisting of P or Q is accepted. If top is accepted, then yeah, this is quite intuitive. I think there's actually two minimal fixed points of the gamma function, one which sets P to top and Q to undecided, and the other one which sets P to undecided and Q to top. So the idea is here that P or Q just tells us to choose one, and the minimality of the gamma function and, well, no, more of the grounded interpretation requires us to choose at most one. So there's really no principled way to choose one of these two, right? So there's no unique grounded interpretation. There are two now. And how we solve this is to come up with a grounded state, which specifies now a set of interpretations that represents the least informative knowledge. I won't torture you now with the technical details, but the idea is that we just generalize the gamma function to allow also sets of interpretations in the input. And then we can just do the same thing as one would do in abstract dialectical framework. So you apply this gamma prime function, this generalized gamma function, to the least informative interpretation. But now you end up in the first step with a set of interpretations, and then you apply this generalized gamma function to the set of interpretations till you reach a fixed point, because this is a informationally monotonic function. In the example we had, for example, we would have P or Q. So we would have in the first step these two grounded interpretations. We would have TU and UT. And then in the second step, we already reach a fixed point, because if we apply the gamma function to each of these interpretations separately, and then we put the result together, we again end up with TU and UT. And so this is the grounded state then. It's just the two interpretations, TU and UT. And so intuitively, the grounded state says you have to accept P or Q, at least one of them, and at most one. Yes, and so we could show about the grounded state that it always exists, it's unique, and we can obtain it in a constructive way by iterating this gamma prime function. And actually the idea of a state, it's not new, and it's not so special or controversial, I would say, because in disjunctive logic programming, people have formulated various well-founded semantics of the same type, where you have a set of interpretations, or where you have as an outcome, if you look at it syntactically, some disjunctions instead of some literals, as in the stable semantics. Yes, so the conclusion, we generalized ADFs syntactically and allow now for indeterminateness, conflicting specifications, and so on. And then the main work was, of course, to generalize faithfully the semantics of ADFs, where now we use 4 truth values instead of 3. As you might notice, the calculating the semantics, it's quite a lot of work. And so we also have implemented the semantics in Tweety. So one doesn't always have to do the work by hand on paper. Open questions which come to mind here, which we want to look at in the future, is of course the complexity of this formalism, and this will also give us a first view on which formalisms we can represent and things we hope to represent in CDF. This was actually one of our motivations for starting to look at this, or representing conditional logics, but also, for example, disjunctive and propositional logic programming, or higher order argumentation. And in fact, what was going on under the hood here is that this is one of the first applications of something that Offer Ariely and myself developed, which is non-deterministic approximation fixed point theory, where we look exactly at this kind of functions like the generalized gamma function, which map one interpretation to a set of interpretations. So I would like to thank you for your attention, and I'm happy to take any questions.